The other problem with bridges is they were very slow. As they learned MAC addresses and forward traffic, they had to look them up, and it was all software based, meaning there's a program installed on side of that bridge that would have to look up the MAC addresses. And it would kind of slow down the network communication, at least compared to a hub, but it was better than having collisions left and right. So that was where the final solution came out, our switches. Switches, first off, split each port into its own collision domain. This is why I nearly had a heart attack at the retail store that shall remain nameless when the guy said, oh, there's no real difference between a hub and a switch, and other than the cosmetics of them. Well, there's a world of difference, because a switch has every single port as its own collision domain, meaning every single device that's plugged into its switch can send at exactly the same time, and you won't have any problem at all. Essentially, when you get rid of all the hubs in your network and replace them with switches, you will have no more collisions, unless there's some kind of major network problem. You will have no collisions at all, and it completely clears up network communication. Second benefit of moving over to a switch is, since each port is split into its own collision domain, it now opens the door to something known as full duplex communication. Meaning, instead of saying our devices will send or receive, they can now send and receive. I don't know if you knew it, but when you bought a network card that is rated at 100 megabits per second for your PC, you are, at no extra cost, getting a network card that can actually do 200 megabits per second. Because all network devices are rated in half duplex, meaning they're rated as send or receive at once. But when we have a full duplex communication or network card turned on, we can actually receive 100 megabits per second, and we can send 100 megabits per second at the same exact time. That's the benefit of full duplex communication. One more benefit of switches is that they now moved all the MAC address learning. You know what bridges were very slow at because they were software based? They moved it into a hardware chip. It's actually known as an ASIC. Now, you won't need to memorize that and know what that is, but you'll hear the term a lot when you're looking at switch statistics. They'll say, yeah, we use ASICs, which stands for Application Specific Integrated Circuitry. It was actually a chip that was created by IBM, which moved all the intelligence of the bridge, which required a software program to run, into hardware. The result is that a switch can move data just as fast as a hub can, which everybody says is wire speed. As fast as the wire can transmit, as fast as your data can get from that computer to the switch, is as fast as it can move it over to the other side. Speed of electricity, speed of light, you could say. So switches have become very fast in just about every network environment. Well, I don't want to generalize, but I'll say most network environments have replaced all of their hubs with switches because the cost of them have come down quite a bit in recent years. All right, last thing we'll talk about as we wrap up this video is how a switch does what it does. How does a switch switch? Well, when you first pull a switch out of the box and you plug it in and you boot it up and you plug all your PCs into it, it has this thing in memory known as a CAM table. Now let me back up a little bit. A switch is said to work at the data link layer of the OSI model because it can see MAC addresses and it can learn them. A hub is said to work at the physical layer of the OSI model because it just sends signals. It doesn't look at MAC addresses at all. It just regenerates electricity and sends it out of port. So when this switch first boots up, it has this thing known as a CAM table. Now, if you're an acronym junkie like me, that stands for Content Accessible Memory. It doesn't really mean anything other than it's a place in memory that it can store MAC addresses. But when it first boots up, it's in memory, RAM. It's clear, it doesn't know anything. So traffic actually has to be sent before the switch can become intelligent. Now let's say computer A up here wanted to communicate with computer B. The first thing it's going to do is, B will have its IP address. A is going to need to know what MAC address it is. So it will send what kind of packet? An ARP. Address Resolution Protocol. It's a broadcast that says, hello, I need to know the MAC address of PCB. Now, an ARP is a broadcast message, and remember, a switch is no different than a hub on that. It's only one broadcast domain, so one broadcast will go everywhere. So all PCs will get that broadcast saying, hello, I'm looking for the MAC address of PCB. But stop right there. Inside of that ARP message is a source MAC address of PCA, so that PCB and all the PCs will know who generated that ARP request, and it will be a destination MAC address of a broadcast. Technically, if you open a packet sniffer, which we'll do in a little bit, you'll see the destination MAC address for a broadcast is all Fs. In hexadecimal, it's everything turned on, all Fs. But when it saw the source MAC address come in port 1 of PCA, this MAC address right there, the switch suddenly became smarter. Boing. Port 1, it said, aha, I've learned who you are, PCA. I've seen that the MAC address 00A0121113321 is located out my port number 1 right here. The switch just became one MAC address more intelligent. Now PCB gets that broadcast and says, oh, they're looking for me. So it responds back and says, hey PCA, here is my MAC address. Suddenly, boing, the switch became one MAC address smarter because it knows now where PCB is located. It remembers port 2. Now it still doesn't know who PCC or PCD are because it hasn't learned their MAC address yet. So if PCA, here's a good certification exam question for you. If PCA somehow knew the MAC address of PCD and said, hey, I'm going to send from a source of me and to a destination of PCD down there, that message will come into the switch. And the switch, since it doesn't know where PCD is, will treat it like a broadcast and send it out all ports except the port it received it on. So PCD will get the message, but it won't be until PCD or PCC respond to that the switch will learn their MAC address and start becoming more and more intelligent. Truth be told, when you boot up a switch, it will probably take that switch seconds. I would even say that's conservative. 15 seconds or less to learn every MAC address of every device that's plugged into it. Because computers are chatty. They're always sending stuff and receiving stuff. So it won't take the switch long to build that MAC address table. And from then on out, when PCA wants to send to PCB, all the switch has to do is take that message in, look at its CAM table, look at its MAC address table, and say, oh, you're just going out here. And it does not disturb any of the devices on the network. This is why this switch is considered to have 4 collision domains. It's separate, it isolates them. Only the traffic that belongs out each port will go out it.